From the vast expanse of space, Earth shines like a brilliant blue marble, a beacon of life in the dark void of the cosmos, a sphere adorned with swirling clouds and continents, each one a testament to the dynamic and ever-changing nature of our planet. The evidence is irrefutable. Our planet is round. Satellite images, taken from various angles and distances, consistently show the curvature of the Earth, a beautiful arc that defines our world. Yet, some cling to the outdated belief in a flat Earth, misinterpreting scientific concepts and ignoring centuries of accumulated knowledge. These beliefs often stem from a misunderstanding of basic physics and astronomy, and a reluctance to accept the overwhelming evidence presented by modern science. This essay will delve into the world of geodesy, the science of measuring Earth's shape, to debunk the flat Earth myth and illuminate the true nature of level. Geodesy, a field that has evolved over centuries, uses precise instruments and techniques to measure the Earth's size, shape, and gravitational field. By understanding the principles of geodesy, we can appreciate the meticulous work that goes into mapping our planet and ensuring the accuracy of our global positioning systems. Through this exploration, we aim to shed light on the true nature of our world, dispelling myths and embracing the beauty of scientific discovery. In everyday language, we use level to describe something flat and horizontal. We place a spirit level on a shelf to ensure it's straight. We imagine a flat surface extending endlessly when we think of a level playing field. However, in the realm of geodesy, level takes on a different meaning. It refers to a surface that is perpendicular to the force of gravity at any given point. Imagine a plumb line, a simple tool consisting of a weight suspended from a string. This tool has been used for centuries in construction and surveying to ensure structures are perfectly vertical. When at rest, the string aligns itself with the direction of gravity, pointing straight down towards the center of the Earth. This alignment is crucial for builders and surveyors to create accurate and stable structures. A level surface is always at a 90-degree angle to this plumb line. This means that any surface that is perfectly horizontal will be perpendicular to the direction of gravity. Because Earth is a sphere, this means that level surfaces are not flat but curved, following the curvature of our planet. This curvature is subtle but significant, especially over large distances. Surveyors must account for this when planning large-scale projects like roads, bridges, and buildings. The concept of using a plumb line dates back to ancient civilizations. The Egyptians, for example, used plumb lines to construct the pyramids with remarkable precision. Today, modern technology has advanced, but the basic principles of gravity and alignment remain the same. Modern tools, like laser levels and GPS systems, have enhanced the accuracy of measurements, but the fundamental idea of aligning with gravity is still at the core of these technologies. Understanding how gravity affects our measurements helps us build safer and more reliable structures. So next time you see a skyscraper or a perfectly level road, remember the humble plumb line and the role it plays in our built environment. It's a simple tool, but its impact is profound, helping us shape the world with precision and care. Flat earthers often conflate level with flat, assuming that a level surface must extend infinitely in a plane. This misconception arises from a limited perspective, ignoring the reality of Earth's curvature. While a level surface appears flat over short distances, over larger distances, the curvature becomes apparent. Surveyors, the professionals who measure and map the Earth, understand this concept implicitly. Surveyors employ specialized instruments to measure distances, angles, and elevations, taking into account Earth's curvature in their calculations. One such instrument is the theodolite, a precision telescope mounted on a tripod used to measure angles in both horizontal and vertical planes. Another crucial tool is the electronic distance meter, or EDM, which uses lasers to accurately measure distances. The transcontinental arc of the parallel, completed in 1881, stands as a testament to the accuracy of geodetic surveying and the reality of Earth's curvature. This ambitious project involved measuring a parallel line across the United States, from the Atlantic to the Pacific Ocean. The surveyors meticulously accounted for the Earth's curvature, demonstrating that a level line on a spherical Earth is, in fact, a curved line. Flat earthers often cite the apparent flatness of bodies of water as evidence for their beliefs. However, this observation is debunked by understanding the concept of the horizon. As we look out over a vast expanse of water, the curvature of the Earth limits our view. Objects beyond a certain distance disappear below the horizon, a phenomenon impossible on a truly flat Earth. Understanding Earth's curvature is not merely an academic exercise. It has practical applications in numerous fields. Engineers designing bridges, tunnels, and other large structures must account for the Earth's curvature to ensure their stability and safety. Navigation systems, from GPS satellites to maritime charts, rely heavily on geodetic data and the understanding of our planet's spherical shape. The concept of level does not contradict the reality of Earth's curvature. It is a fundamental aspect of understanding our planet's true shape. When we talk about something being level, we are referring to a surface that is perpendicular to the direction of gravity at the specific point. This distinction helps us comprehend the spherical nature of Earth. On the contrary, it confirms it. Surveyors and geodesists, the experts who measure and map the Earth's surface, rely on this principle to ensure accuracy in their work. They use sophisticated instruments to measure angles and distances, always taking into account the curvature of the Earth. This meticulous attention to detail allows them to create precise maps and models of our world. A level surface, as understood by geodesists and surveyors, is one that is perpendicular to the force of gravity at any given point. This means that what we perceive as flat or level on a small scale is actually part of a larger, curved surface. This concept is not just theoretical. It has practical applications in construction, navigation, and even space exploration. This means that level surfaces follow the curvature of our planet, a fact demonstrably proven through centuries of scientific observation and measurement. From the ancient Greeks, who first proposed the idea of a spherical Earth, to modern scientists using satellite technology, the evidence has consistently supported this view. Historical measurements, such as those conducted by Eratosthenes, who calculated the Earth's circumference with remarkable accuracy, laid the groundwork for our current understanding. The flat Earth myth, while persistent, crumbles under the weight of overwhelming evidence. Despite the proliferation of misinformation, the scientific community has amassed a vast body of data that unequivocally supports the Earth's roundness. Geological surveys, satellite imagery, and even simple observations, like the way ships disappear hull first over the horizon, all reinforce this reality. By embracing the true shape of our planet, we gain a deeper appreciation for the wonders of the cosmos and the power of scientific inquiry. Understanding that we live on a spherical planet opens up new perspectives on our place in the universe. It allows us to appreciate the delicate balance of forces that govern our world and the intricate dance of celestial bodies. This knowledge not only satisfies our curiosity, but also drives technological advancements and inspires future generations to explore and discover. Alright, let's talk about triangles and their angles. In flat or Euclidean geometry, we learned that the sum of the interior angles of a triangle always equals 180 degrees. This is a fundamental rule that holds true for any triangle drawn on a flat surface. Here's a simple triangle. If we measure the three interior angles, let's call them A, B, and C, we find that the sum A plus B plus C is always 180 degrees. This is true regardless of the shape or size of the triangle, as long as it's on a flat plane. But what happens when we draw a triangle on a curved surface, like a sphere? This is where things get interesting. On a spherical surface, the rules of geometry change. Let's imagine we draw a triangle on this sphere. To keep it simple, let's consider a triangle formed by connecting 3 points on the equator and a line of longitude. In this spherical triangle, the angles are much larger. In fact, the sum of the angles of a triangle on a sphere is always greater than 180 degrees. Why is that? To understand this, we need to think about the surface of the sphere. When we draw a triangle on a sphere, we're working on a curved surface, not a flat one. This curvature affects the angles. For instance, let's take a triangle with vertices at the North Pole and 2 points on the equator. The angles at the equator can each be 90 degrees, and the angle at the North Pole can be less than 90 degrees, resulting in a total angle sum greater than 180 degrees. This difference arises because on a sphere, the shortest path between 2 points is an arc of a great circle, not a straight line. When these arcs intersect, they create larger angles than those formed by straight lines in Euclidean geometry. So, on a sphere, the sum of the angles in a triangle can range from just over 180 degrees to nearly 540 degrees, depending on the size of the triangle. This is a key concept in spherical geometry and is essential for understanding navigation, astronomy, and even the shape of our planet. To sum it up, in flat geometry, triangles always add up to 180 degrees. On a spherical surface, the angles of a triangle add up to more than 180 degrees. This crushes flat Earth, and anyone with half a brain realizes this. This difference is due to the curvature of the sphere, which changes the nature of the angles formed. Understanding these concepts helps us see why flat Earth arguments about geometry don't hold up. The Earth is a sphere, and spherical geometry is crucial for accurately describing its surface. Thanks for joining me today. If you enjoyed this video, don't forget to like, subscribe, and leave your questions in the comments. See you next time. Please consider subscribing for more videos. And remember, you're not stupid because you're a flat earther. You're a flat earther because you're stupid. Peace.